Welcome to Physics 2. All right. I updated my system slightly, so I got a Blackmagic camera. So now the quality of the video should be better. So it's a course about electricity and magnetism, right? Before we start discussing physics, a few words about the course structure. And guys, if you need to ask something, if something not clear, don't be afraid to interrupt me and ask questions, right? Although try to keep your mics off, right? It looks like somebody's mic is okay. Okay, I muted one. Yeah. So a few words about the course structure. So all information about the class I usually keep in this course web page and Blackboard. A couple of years ago, I tried to post everything both in the course web page and the Blackboard, but it's extra work. So as a result, eventually, please, somebody's mic is on, right? Now I keep when semester starts. When semester starts, I keep all information on the Blackboard, and I use the course web page before beginning of the semester because Blackboard is not available, and everyone can see what is in the course web page, right? But now semester started, and you can find all the information on the Blackboard. What do I usually post here? First of all, there is a folder lecture notes. Before each class, before each lecture, a night before, I usually post pre-lecture slides. Basically, my slides, but I usually remove clicker questions and examples, right? So you can use those slides. And even in the morning, I forgot to post it last night. In the morning, I posted pre-lecture slides, so you can even now get that. But then after the class, after the lecture, I post the whole lecture. Also, after the class, I usually put the video together and a link will be there. Right, then there will be a folder full of links to mastering physics, to do homework, right? I will discuss that on the next slide. Then there will be plenty of other, for example, course policy, information about the book, so you can see. Then folder with exams from the previous semester and so on. Yeah, you can, it's not that complicated, you will find it all. Okay, so about the homework. So homework will be done online, all right, using Mastering Physics, right? And so here is the course name and course ID to register. In order to register to Mastering Physics, you need to go through Blackboard. Don't go directly to Mastering Physics, right? So you need to go to the Blackboard, find that folder, Mastering Physics, dive in, and there are tons of links. You can click on any of those links, and you will be guided through the registration procedure. Of course, at some point, you will be asked, do you have an access code? So if you bought a book, right, so a book, textbook, goes with access code, and you can use that code for a couple of years, I think, right? So if you use the code in Physics 1 class, yeah, you can still use it. You can still recycle it, right? Again, registration must be done through the Blackboard. Because every semester, plenty of students send me emails, I cannot register, why? Because most of the time students go directly to Mastering Physics. So don't do it. So usually homework will be due Sunday midnight. Usually one homework per week. Right? Occasionally, if we're kind of maybe slower than I expected, yeah, I can postpone homework till maybe Wednesday or Tuesday, right? But of course, in that case, I will announce that, I will tell you. Right? But usually Sunday midnight. There will be like 6-7 problems per week. Okay, attendance. Lecture attendance will be checked, right? And of course, attendance maybe like once in a couple of weeks I will post in Blackboard, right? Again, the code is over here, right? You see 1655, and here's the address to that app, right? where you have to go and enter the access code. And as I said, once in a couple of weeks, I will go and download all the results. Since some students are registering, some students are dropping the class, usually first 2 or 3 classes, I don't count towards attendance, right? And then after 2 or 3 classes, yeah, I'll start counting attendance. So the book, all right, here's the book, all right, by Randall Knight, Physics for Scientists and Engineers, right? Okay. I don't force students to buy this book. Okay, we actually use the 4th edition. So if you want to save money, you can use the 3rd edition. It's pretty much the same, right? The content. They just move the chapters around, change the photographs. Instead of photograph of an old keyboard, now they use photograph of a fancy Apple keyboard. But book is pretty much the same, right? But of course, since information is shuffled, of course, you have to be sort of responsible to find the correct information in the older edition. If you feel very comfortable, right, in terms of math and physics, your skills, right, you can use any other book. I don't force you to buy this particular book, right? But what you need to have access code, right, in order to do your homework. And if you didn't buy the book, you can still get the access code during the registration. All right, again, during the registration, at some point you will be asked, do you have a code? If you have, enter. If you don't have, you will be offered to buy it. Right? Okay, so there are plenty of activities on in the chat. Right. Okay, no, it's difficult to lecture and read at the same time. So usually I don't read the chat during the lecture. So then, what else? Quizzes, right? Quizzes, I started practicing quizzes in this format in the previous semester. Quizzes are done outside of the class. Usually, I give a little bit more challenging problem, and I usually give like maybe a day or 2. And I usually, of course, announce, okay, so tomorrow I will give you a quiz, and then you will have to submit your solutions by, let's say, Wednesday, right? So everything will be announced. Some students in evaluations, they complain, why don't you announce the quizzes from the very beginning of the semester? No. I'm not giving you pop-up quizzes, but if I give you 1 or 2 days to solve a particular problem, it should be enough, and you should be able to find the time, right? So I'm not going to announce quizzes from the very beginning of the semester. Usually, I offer like 6 or 7 quizzes per semester, right? And we use GradeScope, all right? So when you solve the problem, quiz, scan it and upload to GradeScope. GradeScope link to the GradeScope again can be found in Blackboard, right? So there is a blue button on the left side of the screen. So click and you will be guided to the GradeScope, right? So when we get to the quiz, of course, I will send you an email with some explanations about GradeScope. But I'm sure that most of you are familiar with that. So yeah. Is there a question? Okay, no questions then. So homework quiz. So there will be 2 midterm exams. Exam dates you can find in the course policy. I tend not to change those dates, so don't plan any traveling, right, or any events on those days, right? And the final exam. Lecture attendance I already mentioned, so you see percentages, and then you can see the grade conversion table, right? So you can read it by yourself. Okay, so that's it about the course structure. And so let's start. So we'll start with chapter 22. It's the beginning of volume 2 of the book. So first, no, you know what, before I start going into the details, so in this course, what we're going to cover, first we will start with electricity, and we will spend plenty of time discussing only electricity. Then we will move to magnetism. Then after that, we will finally write down the foundation of electromagnetism, which is basically Maxwell's equations. Right? And then after that, we will move, make a transition, I hope smoothly, into optics. And the last couple of weeks of this semester, we're going to discuss wave optics and ray optics. So that's the scope of this class, right? Okay, and now I'm supposed at this point to say something banal like, okay, electricity is everywhere, right? And it's worth of studying, right? That's why it's one of the required courses, because you need to have some basic ideas of electricity and magnetism, electromagnetism. So, of course, first we will discuss what is called electrostatics, because it's the simplest situation when interacting charges are stationary, when they don't move. It's a simplest situation. And then, of course, we will start making a picture more and more complicated, right? And, of course, the first question should be, what are the sources or a source of all electric and magnetic phenomena, right? And in order to answer the question, we need to, of course, recall classical model of an atom, right? Of course, you are familiar with that. So at the center, you have a nucleus, right? And there are some particles orbiting around that nucleus. Particles orbiting, we called electrons. Just nice name, right? Why not? And electrons are negatively charged. If you ask me why they are negatively charged, I wouldn't be able to answer, because it's basically by convention. So what does it mean by convention? You know, a bunch of old physicists got together somewhere in Florida, right, and decided, okay, let's call electrons negatively charged particles, right, and force the rest of the world to follow that convention, right? It's basically by convention. And in the nucleus, there are two types of particles. Neutrons, they're electrically neutral, so we're not going to talk about them, maybe occasionally. And of course, the second type of particles, protons. Those are positively charged particles, again by convention, right? Of course, all these conventions happened a couple of hundred years ago. So they could name them sort of in in opposite way. Electrons positively charged, protons negatively charged, and the whole picture, the whole structure of electromagnetism would be still the same, right? So by convention, electrons are negatively charged, protons are positively charged particles, right? So you see, by convention. Okay, so now, and of course, so these particles are the sources of electricity and magnetism, all electromagnetic phenomena. So they are troublemakers. So now, observations. So now we know the sources, and of course, you can start playing with them. So what can we observe playing with them? So if you take, for example, no, first of all, of course, you will notice that they interact. You know what, let me mute my speaker right on my main computer, because you're chatting, and every time Microsoft Teams announced that something happened in the chat. All right, so they interact. And if you take, for example, two like charges, right, for example, two positive charges, two protons, they repel. They hate each other. They want to be as far as possible from each other. So it's an observation. So like charges repel. The same would happen, of course, with negative charges. Then, of course, if you take two opposite charges, positive and negative, of course, it's a pure happiness, right? Pure love. And, of course, they attract to each other. They attracted to each other. All right, so we can, of course, generalize, and we can say that opposite charges attract. Okay, so that's the observations, right? On the level of blah, blah, blah. But of course, we all here, I know, future physicists, engineers, chemists, right? Of course, we want to be quantitative, right? So we're not philosophers. So we want to get an expression, a strict definition. So we need to describe these interactions using a formula. And first of all, which quantity do we use to describe interactions? From Physics 1, you should remember that in physics we use force. Force is the quantity which was introduced to describe any possible interactions in physics. Pushing, pulling, kicking, right? All those physical processes in our world we describe using forces, right? So since these charges interact, so we need to introduce an expression for a force, electric force. And of course, you understand that I'm moving towards Coulomb's law. Right? So Coulomb's law. So first of all, so we need to understand and remember that Coulomb's law works for point charges only. If you have two massive, I don't know, charged balls next to each other, you cannot use just Coulomb's law. In that case, you will have to do some complicated integration, right, in order to calculate the forces they exert on each other. So Coulomb's law for point charges. If your Q1 and Q2 point charges at the distance r, then yes, you can use Coulomb's law. Of course, first of all, about the notation. So in this case, charge 1 is going to exert force on charge 2, and we can denote it as F1 on 2, or sometimes just use the subscript 1, 2. Right? And at the same time, the second charge is going to exert force on the first charge, F2, 1. If I ask you the question, what about the magnitude of this force and that force? They must be the same, according to the Newton's third law from physics 1, right? And it doesn't matter, for example, this charge can be gigantic, this charge can be small, still. This force and that force must be the same. Some students still make these mistakes, like occasionally in the past I would give some simple question in a quiz, like there is a charge 4Q, there is a charge Q, draw forces. And still plenty of students draw one vector is much larger than the other one. No, forces must be the same. Accelerations, of course, will be different, but forces must be the same according to the Newton's third law. Right. Okay, so and Coulomb managed to write this expression. It's a fundamental equation. It means, what does it mean? It means that it cannot be derived. It's basically written based on observations. No one can derive this. Bunch of data were collected, and then they played with these quantities to get something which fit that data. And this equation works. Coulomb's law. So these forces, magnitude of these forces, proportional to the product of the charges, inversely proportional to the square of the distance between them, and they introduced a coefficient of proportionality. There is no special name for that k, it's just k, right? And the value is large, almost 9 times 10 to the power of 9. All right, and you see those complicated units. Newtons meter squared divided by Coulomb squared. And of course, units of charge, coulombs, you all know that. Then, also, physicists, for whatever reasons, introduce a different constant, permittivity constant, epsilon naught. You can think about this constant epsilon naught as the constant which describes electric properties of a vacuum. Maybe in a month, when we will move to magnetism, we will introduce permeability mu naught, and that constant is going to describe magnetic properties of a vacuum. This describes electric properties of a vacuum, right? And of course, this constant epsilon naught and this constant k are connected, and they're connected in this way. 1 over 4 pi k, it's epsilon naught, and you see the value of that epsilon naught. And of course, in terms of this epsilon naught, the Coulomb's law is going to look like this. What should be the first reaction of any normal person by looking at this formula? And I'm sure that you're all normal, right? Look, you must be really crazy, or I don't know, cuckoo, right, in order to introduce a constant like this, 1 over 4 pi epsilon naught. Why would we introduce this epsilon naught in order to have this crazy looking constant, when we can have just k? And the reason is, in a couple of classes, we're going to introduce Gauss's law. And then we will see that this Coulomb's law and Gauss's law can be used to introduce the electric field, or to calculate the electric field, right? And Gauss's law looks much better, much simpler, elegant, right, beautiful, right, in terms of epsilon naught. Gauss's law will look much better using epsilon naught. But Coulomb's law looks ugly in terms of epsilon naught. But if you want to use Coulomb's law looks great using k, but it looks ugly using epsilon naught. But the Gauss's law would look ugly if you use k. So it's just if you want to use Gauss's law, epsilon naught is better. If you want to use Coulomb's law, K is better. All right. So of course, don't use this 1 over 4 pi epsilon naught. It's too much trouble calculating. All right. Okay, so that's Gauss or Coulomb's law. And now, of course, if you look at the expression for the Coulomb's law, of course, it should remind you something. It should remind you force of gravity, gravitational force. The structure is very, very similar, right? The difference is mainly in the constant. You remember the constant, gravitational constant, that G. It's a 6.67 times 10 to the power of minus 11. You see, G, right? And this is K. Here, 10 to the power of 9. Here, 10 to the power of minus 11. It's a gigantic difference. So K is huge. G is teeny tiny. As a result, gravitational force is much, much, much weaker than the electric force. For example, in order to demonstrate its weakness, let's look at the hydrogen atom. Hydrogen atom is just basically inside in the nucleus we have one proton and electron orbiting that proton. And of course, since these two particles, they have masses, of course there must be gravitational interaction between them, right? So there must be gravitational force on top of electric force, okay? So now let's compare these two forces. Let's look at the ratio of the electric force versus gravitational force. And I started with, I don't know, what about 100? We can easily add more. And it's still not enough. And we can add tons of other zeros. So eventually, the ratio is 10 to the power of 46. It's a huge difference. That's why whenever researchers, right, physicists, chemists describe some molecules or some atoms, they never even consider gravitational force because it's a teeny tiny. So every time they only work with the electric force. So electric force is way, way, way larger than the gravitational force. Actually, the force of gravity is the weakest force in the universe. And of course, it doesn't mean that the electric force is the strongest in the universe. There are two other forces which are stronger than the electric force, right? But anyway, electric force is significantly larger than the gravitational force. So it's a first difference between these two forces. Second one, the second difference, major difference. Have you ever seen a repulsive force of gravity? It sounds even strange, right? Because all the time, masses are positive. We don't have negative masses, right? As a result, force of gravity, only a force of attraction. But electric force, of course, it can, charges can attract, and of course, charges can repel, as we saw in the previous slide. So these are two major differences between these two major forces. Okay, so now it's time probably for a, no. Okay, one more slide. So now we know how to describe interactions between 2-point charges. What about if you have more than 2-point charges? What if you have 3-point charges or 4-point charges? How can we find, for example, the net force on one of those charges? And in this case, of course, we can use a powerful principle of superposition. No one can prove it, but we all use it. Almost everywhere it is being used, right? Principle of superposition. Of course, you all know that you used it a lot in physics 1. So but in this case, so if you have, for example, let's say 4 charges, and let's say these 4 charges interact with this charge Q, red one. And let's say we want to know the net force acting on this red charge Q. So procedure is straightforward. First, you take, for example, these 2 charges and apply Coulomb's law. You can calculate force F1. Then you can take these 2 charges, again, Coulomb's law, F2, then again Coulomb's law, 4 forces. And now the second step, principle of superposition. Basically, it means that you just need to add these four forces as vectors in order to get the net force acting on this red charge. Right? Okay, so again, it's a very, very powerful principle. Of course, we're going to use it, and we already used it in our first recitation class, and some of the recitation classes were yesterday. Some of you are going to have it today. Right? Okay, so next question for you. You already chat a lot, and so in your chat, you have to scroll it down significantly in order to see the first clicker question. Right? Yeah, the first class usually full of discussions in the chat. Okay, so you see there are two questions. First, concept test 1. The second is, well, of course, will be concept test 2. The first one. So what do we have here? We have three charges. So this plus Q, plus 2Q, and plus 4Q. They are at the same distance. You see D and D. And of course, this plus 2Q is going to exert force on this, and this plus 4Q is going to exert force on the yellow charge. So the question is, of course, there will be some net force acting on plus Q. So the question is, which vector out of these five best represents a direction of the net force acting on this charge plus Q? So you see 1, 2, 3, 4, 5. So which vector best represents the direction of the net force acting on this charge plus Q? Right. Again, so the poll is in the chat. I'll give you, a minute, right? Maybe less.
I don't see it.
You just scroll, go to the chat, and scroll it up because you chat a lot, guys, almost to the top. Scroll all the way to the top.
And there it is. Thank you.
Yes, and you should see those two polls. So that's how in mastering physics works. I have to post it into the chat. Okay, I need to move myself slightly. I want to see the answers. Okay, I found it. Okay, I see it works. I see the leader, B, then C, D. Okay, so let me look at your answers. Yeah, most of you believed in B. All right, some believe in C, and a little bit of students believe in E. Okay, so let me discuss that quickly. Right. Yeah, it's not that complicated question. So I open exactly the same picture, but over here, right? And so let's first consider these interactions. So, of course, this charge plus 4Q is going to exert force. Of course, that force is going to be a repulsive force because both of these charges are positive, right? Like charges. So the force, let's assume that this is a vector representing these interactions, right? Then, so this charge, of course, is going to exert also a repulsive force, right? But since distances are the same, but this charge is smaller than that one by a factor of 2, of course, the force will be smaller by a factor of 2. So now we just applied Coulomb's law twice, and now the second step is principle of superposition, right? So you need to add these two vectors as vectors, right? Using a parallelogram method, right? So as a result, you will get a vector, right, pointing that way. So this angle will be actually 60 degrees. That angle is 30 degrees. So the best vector 2 will be the best one. So, of course, the answer is B, right? Vector 2. All right, okay, so it's simple, all right? And most of the questions actually are not going to be complicated, right? Now, very important fundamental law, conservation of charge. Okay, I created some kind of bunch of pictures. So let's assume that we have some treasure box, right? And let me drop into this treasure box a bunch of particles. Some of them neutral, some of them neutrons, protons, electrons, right? Just a bunch of charged and not charged particles, right? And close that box, and let's wait, for example, for a year. Why not? If we open that box up, of course, we will see that the amount of charge will be still the same Q. Of course, you can, first response should be, yeah, of course, since number of particles, number of particles are going to be the same, right? But no. Strictly speaking, number of particles in that box can change, and most likely will change, strictly speaking. But the total charge will be still the same. For example, one of the examples, what might happen to, for example, a neutron. Let's say if you have one of those particles is a neutron, within 100 seconds, it can create a proton, electron, and antineutrino. Number of particles increased, but the charge still the same. So neutron was electrically neutral, and these three particles is going to give us a net zero charge. So number of particles in this box can change significantly, strictly speaking, but the total charge will be still the same. So that's why there is no conservation, there is no law conservation of particles, but there is a law conservation of charge. So we're going to use this law, of course, a lot, often, and no one has ever seen in examples where conservation of charge fails to work. Right. Of course, if you find that, you will be famous, and Olney Hall will be renamed after you. Right. So, conservation of charge will be used, of course, a lot. Okay, and now after this, now we need to start introducing one of the most important quantities in electromagnetism, the idea of the electric field. Right. Okay, so now it's electric field is introduced basically at the end of chapter 2 and in chapter 23. So first, what's the idea of the electric field? So you remember in physics 1 that we had different forces, and some of them we called contact forces, for example, like tension, friction, normal force, and sort of it's not that difficult to get the idea of those forces, and because there is a direct contact between objects, right? So sort of like I'm standing right now on the floor, there is a direct contact, and as a result, floor exerts normal force on me, right? So yeah, I can sort of conceptually understand that. But what about cases like this, right? When we have the Earth, the Moon, no contact, but of course still there is a force. Or like in this case, right, no touching, but still there is an interaction. They exert forces on each other. Of course, back then and still now, you can ask tons of questions. And those questions, for example, like how fast it happens, this interaction. So are they exchanging some particles, or are they distorting some space, or are they creating waves to exert those forces? You can ask tons of reasonable questions. And most likely no one will be able to answer those questions, right? So what do we usually do if we cannot answer the question? Politicians, they would usually just answer something else, right? Or they will start answering in such a way that you will get lost very quickly, right? Physicists, they usually sort of try to sweep all those questions under the rug, right? But of course, the rug must be nice, Persian, right, fancy, so that no one would even dare to lift it and ask those questions again, right? So what do I mean by that rug? In this case, since there is no sort of kind of direct interactions of the Earth and the Moon, physicists introduced the third party. What do I mean by that? Okay, the first party, of course, the Earth. The second is the Moon. And the third party is some kind of gravitational aura around the Earth. Gravitational field. And now, once you introduce that field, which fills pretty much the whole space, right? All the way to infinity. And now that moon can interact directly with that gravitational field. So at that point where the moon is, of course, there is a field. And as a result, now we kind of have a direct interaction between the moon and the field. So now we're kind of trying to hide all those questions, right? And of course, we all know that actually interactions between, for example, gravitational interactions between the objects are not instantaneous. It propagates with the speed of light. If, for example, you, let's say, you have the Earth and the Sun, and let's imagine you slightly displace the Sun, it will take 8 minutes for the Earth to respond. And of course, the Earth will also be displaced slightly, right? So all this doesn't happen instantaneously. There's no magic distant interactions. No, there's most likely exchange of something, right? It's only shaman can believe in some magic distant interactions dancing around the fire, for example, right? But of course, these mechanisms are quite complicated, and we cannot answer those questions, right? But introducing the idea of the field helps a lot, right? So that's the, again, idea of the electric field. But of course, it's on the level of blah, blah, blah. But again, we need to introduce, we want to be quantitative, and of course, we need to introduce expressions so that we can calculate that this field is stronger, this field is weaker, right? So we need an expression, right? So now, what can be used? How can we define the electric field properly, not just in the words? Okay, so all right, the question. And so now, in order to define electric field, so let's look at some particular example. Well, let's say we have this charge Q capital, which is a source of the electric field, this electrical aura, right? Okay, this is electrical aura, right? This cloud. And of course, so what we want to define electric field. Basically, we want to measure, we want to probe. In order to do that, of course, we need to have some probe system. As a probe system, there must be some object which are sensitive to the presence of the electric field. And of course, it must be simple. So what can be simpler than a point charge? So let's take this point charge and use it as a probe charge to define the electric field, to probe it. And now, again, in terms of expression, it must be defined. So what can be used? So far, we don't have much. We have only one expression, Coulomb's law, right? So let's look closely at Coulomb's law, and actually let's try to use it in order to see what is not good about using Coulomb's law to define electric field. We will see how we should adjust that Coulomb's law. But first, let's just try to use Coulomb's law. Okay, and let's imagine this situation. Let's say me and one of you, we work for the same boss, right? And the boss told us, okay, so here is the source of the electric field, right? Go and measure the electric field at, for example, this particular point. Okay, I will check my pockets and I will get, for example, let's say this is my probe charge. I will take my probe charge, let's say 1 Coulomb. Go, position it at that point where we want to find the electric field, and use this formula, and I will get, of course, some, let's say 1 Newton force. Again, I want to try that. What if I use that expression to define electric field? Okay, so that will be, I will write the report, and in my report, the field will be 1 Newton on that particular point. Let's say now, your turn. You have bigger pockets now. Let's say you have 5 Coulomb charge, probe charge. So that's what you have. You will go again, position this 5 Coulomb charge at the point, and of course your force, which you want to use as the electric field, of course, will be 5 newtons. You will write your own report, and what will be the response of the boss in that case? 2 reports, in one report the field is 1, in the second report the field of 5. Of course, what will be his response? What, are you completely crazy? How come that the value of the field at the same point has 2 different values? It shouldn't be like this. It must not be like this. But if we look at the ratio, for example, let's say this force F versus charge, and in this case, F versus charge, we will get exactly the same number, 1 newtons per coulomb. So basically, we need to eliminate the value of the probe charge from this game in order to define electric field, so that it would be unique number at each point. So that's why electric field is introduced as the force acting on the probe charge divided by the value of the probe charge. So that it doesn't matter which probe charge you have in your pocket, everyone will be able to get exactly the same value of the electric field at a particular point, of course. So we need to remove the value of the probe charge from this picture. So that's the definition of the electric field. But it's not the whole story. Now we need to impose a few restrictions. First of all, first restriction. What if you use positive probe charge to find the electric field? In that case, this charge is positive, that charge is also positive, so the force will be that way, right? Force will be that, okay, away. The force will be away, and of course the electric field will be also that way. Okay, but what if you have a negative charge? If you use negative charge, force will be a force of attraction, and the electric field will be that way, opposite direction. So we're getting ambiguity. All right? So, and we shouldn't have any ambiguities. To remove that, we're going to impose the first restriction. Everyone in the world who wants to measure, probe, define the electric field must use a positive probe charge. Convention. If you don't want to create confusion and troubles, you must use a positive probe charge every time to define electric field, to measure the electric field. So it's a first restriction on the probe charge. The second one, what if we have, for example, these tennis balls, they are green, that's why the green screen effect removes them, that's why they're transparent, right? All right, so let's say this charge creates the electric field, right? And let's say this is our probe charge, and they're comparable in size. The value of the charge comparable. So if we take this probe charge and bring it here to measure the electric field, what will happen to the source of the electric field? Of course, they interact. And the source of the electric field most likely just fly away, right? Because this probe charge basically pushed that charge which created the field, away. So basically we destroyed the system, electric field of which we wanted to measure, or maybe significantly changed. Of course, you all know that during any measurements, we intrude in the system. We slightly disturbed it. But of course, every time, that disturbance must be as small as possible within experimental error, so that you would not change a system significantly. So in order to avoid doing it here while we measure the electric field, we must impose the second restriction. The probe charge, a probe charge, must be small, so that the electric field of which you want to measure wouldn't be changed significantly. It's like, let's say you want to measure the temperature of water in a bucket, all right? So you're not going to bring a gigantic thermometer to stick it in, because in that case, the temperature of thermometer is going to change temperature of water significantly. No, we don't do that. We usually come with a small thermometer, stick it in. Of course, even that thermometer, temperature of that thermometer is going to change temperature of water in bucket, but it will be very, very small change within experimental error. As a result, our measurements will be more or less nice. Right? So now the second restriction, a probe charge must be small. So now these three pieces gives us definition of the electric field. So now we can put a tag, yeah, hello, my name is electric field. Okay, it's one of the, okay, let me hold it for a couple of seconds in order to finish this slide. So now we introduce one of the fundamental quantities in physics and of course in electromagnetism. So now units. There is no special unit for the electric field. Although it's one of the fundamental quantities, it feels so unfair, right? Fundamental quantity and there is no special SI unit. So whatever we see here, newtons divided by coulombs, that's units of the electric field. And it feels even worse because in a month when we get to the magnetic field, also magnetic field, electric field, they're both fundamental quantities. But there is a special SI unit for the magnetic field, Tesla. We will see it in the future, right? But there is no special unit for the electric field. It's a pure discrimination of the electric field. All right, so I posed that picture, right? And the reason is because we introduce special units for a quantity if that quantity is used a lot. Right? Because if we start introducing a special unit for every quantity we introduce in physics, we're going to have a big pile of units. It will be very confusing, difficult to remember. So usually in physics, we try to introduce new quantity only for a quantity which is used a lot. Electric field, yeah, it's very important, but most of the time it is used by physicists or hardcore physicists. They don't use electric potential, for example, theoretician. No, every time they use electric field, right? But magnetic field, since magnetic field is involved in production of electricity in all power stations, we will see that in a month maybe, right? So since it is involved in production of electricity, so in order to simplify lives of those engineers who has to use electric field a lot, a special unit was introduced, Tesla. Otherwise, it will be a complicated construction of other units, right? So that's the logic. Otherwise, it's a pure discrimination of the electric field relative to the magnetic field. So electric field doesn't have a special unit. Okay, at this point, I wanted to finish this class. And okay, so if you have questions, you can ask. Otherwise, some of you I will see tomorrow, and some of you I will see on Thursday.